for being here today. It's exciting to look at the list of participants. We have folks from all over the US and all over the world. So welcome. And I'm really excited to have you in the workshop for the next 3 days. We are going to start with a kind of very brief overview of kind of all of the topics that we're going to talk about. And then we'll dive right into an introduction to linear regression. I assume for most of you, linear regression is something that you've covered before, but just to make sure that we're on the same page in terms of the words that we're using and the kind of basics that we're building off of for mediation, moderation, and conditional process analysis. So I want to start off with an example. And this example comes from a paper that was published in the Journal of Marketing Research in 2008. And this was a pretty basic experimental study where they were really interested in consumer evaluations of products, and particularly how the packaging of those products can impact the consumer evaluation of the product. So this is kind of interesting from a marketing perspective because you don't actually have to change the product. You could just change the packaging, and that's easier sometimes. And they were really interested in this idea um, of art as being part of a specific of being part of the packaging. Because there is some theory that suggests that people kind of assume that art means things are a luxury. So they essentially randomly assigned each participant to look at this set of silverware. And the silverware was either packaged with a picture of a cafe scene. Can you guys see my mouse? It seems like you can. Okay, cool. A picture of a cafe scene, which is on the left, or a painting of a cafe scene, which is on the right. And then they were interested in the consumer's evaluation of these, of the silverware. So the basic idea here is that we're interested in the role that the packaging plays in the product evaluation. So here on the left is our kind of explanatory variable or the manipulation in the study, whether it's a photo or a painting. And then we're interested in how that predicts the product evaluation of the silverware. So the product with the painting on the box was evaluated more favorably than the product with the photograph. But once we know that, we might have a lot of follow-up questions. So for example, we might want to know, how does that happen? What's going on in a human's brain that they can see two relatively similar images on the front of a packaging, and that affects their evaluation of what's inside of the packaging, right? The silverware hasn't changed. So we would hope that people's evaluation of the silverware is independent of the packaging. Maybe as consumers, we might hope that. As marketers, we might hope that the packaging does impact the evaluation. So this brings up this question of mechanism. What is going on when we see a photo or a painting that is then changing our evaluation of the product? We might also want to know whether this kind of manipulation works across other kinds of products. So does this just work for silverware? Is there something magical about silverware? Or does it work differently for different kinds of consumers? And these are the kinds of questions, these follow-up questions that we'll be focusing on in this course. So an example of a mediation analysis is getting at this question of why or how, where we might think that, well, maybe by putting a painting on the silverware packaging, that is increasing the perception that this item is a luxury good, meaning that it's not really necessary. It's something that is kind of an add-on. Right. So when we see the painting, we might evaluate this set of silverware as a luxury good, and then that increases our evaluation of the product. And oftentimes, product evaluation is measured in how much people are willing to pay for the product. So this is an example of a potential mechanism where we think, okay, well, what is it that the painting is doing? The painting is increasing our perceptions of luxury, and we rate higher luxury items as more high quality. And this is a quantification of this effect would be called an indirect effect, which is what we'll focus on in our mediation section. By contrast, we might think about other questions like when or for whom, under what circumstances does this effect occur? And what we might see is that there are variables that moderate the effect of the manipulation on product evaluation. So, an example of this might be household income, where we might want to know if this art manipulation is larger or smaller for individuals with higher or lower income. We want to know if the size of the effect of the painting on product evaluation depends on or is a function of income. And in this case, we would call income a moderator of the effect of the art infusion manipulation on the product evaluation. And moderation analysis is really all about estimating these contingent effects, meaning we might want to estimate what is the effect of the manipulation for people with high income, for people with middle income, for people with low income. And we can use this to examine the boundary conditions of effects or the relationships that we're looking at to understand when they are large versus small, positive versus negative, zero versus non-zero. And moderation is a really powerful tool, especially when used in combination with mediation. So, for many of you, you may have done mediation or done moderation before, and you're really here for the combination of the two, which is sometimes called moderated mediation. In this class, we'll mostly call it a conditional process analysis. But the basic idea is that we can combine mediation analysis and moderation analysis together to understand the contingencies of processes. Because when we do a mediation analysis, we're assuming that every single individual uses the same process. And that's often not the case. It might be that some people of certain groups use a different process than other individuals, or that it varies along some continuum, like household income. So in our example here, we can combine our moderation analysis and our mediation analysis to understand how the indirect effect of the art manipulation on product evaluation through perceptions of luxury might then depend on household income, where we think, well, maybe this manipulation only affects perceptions of luxury for individuals who are not as familiar with luxury goods, i.e., individuals with lower income. And in this case, we can actually estimate whether or not the indirect effect depends on the moderator and what the size of those indirect effects are for anyone at any given household income. And what this does is it allows us to estimate complex models that align with our theories and think about cases where the mechanism may depend on some other variable. In other words, that the mediation is moderated. So in this course, we're going to be covering mediation, moderation, and conditional process analysis, and we'll be doing examples of each of them, and hopefully kind of whatever it is that you came for, whether you're like, I'm already an expert in mediation, you're going to be here sticking along for the conditional process analysis. And I imagine even those of us who are feeling like experts, there's always something to learn along the way. I always tell my graduate students, I think I took intro grad stats like 4 times over the course of my life, and I learned something every single time. So even if you're familiar with some of these analyses, I imagine that you will be learning quite a lot in this class, and I'm really excited to have you. So I want to talk a little bit about what we will do in this class and then what we won't do in this class so that your expectations are set. We're going to start with an overview of ordinary least squares regression. And this is just to make sure that we're kind of all on the same page in terms of the language that we're using as we set off into our adventure of statistical mediation analysis. And the core here is we're thinking about how do we estimate and make inference on direct, indirect, and total effects? And if those words are totally unfamiliar to you, that's okay. We will be defining those as we get to that section. In this section, we'll mostly be using ordinary least squares regression. At the end of the last day, I have a little section on what are some of the difference between the regression approach that we're using and structural equation modeling approaches. So if you're curious about those differences, that's something that we will be talking about. After we cover mediation analysis, we're then going to move on to moderation analysis. And this is again all about estimating and interpreting models where we have contingent effects, i.e. the effect of some variable on an outcome depends on a third variable. And then we're going to combine these two things together into conditional process analysis, where we will look at examples of a mediation being moderated, and we'll look at different combinations of where in the mediation the moderation occurs and how you make that decision. And then kind of depending on how much time we have on the last day, what I might do is on the end of the second day, I'm going to take a little poll and see if there are some advanced topics that you guys are interested in that we can cover on the last day, such as multiple mediator models or multi-categorical independent variables or repeated measures mediation. So whatever the group decides. Wonderful. So what you'll need in this class is a computer. Hopefully you're all on a computer because I think you're here on Zoom, so that's usually covered. We're hoping that you can follow along with the code, and we'll have a couple breaks in the day. So we have a break kind of in the middle of the day, but also we have, we're going to do a short break in the morning because the morning session is a little bit longer. And for some people, trying to follow along with the code while I'm talking, it's a lot and you get a little lost. That's okay. One thing that you can do is either in between the days, go back and practice the things that we tried during the day, and then come in the morning with questions about what you tried. And then we will also have specific sections where we're doing little activities where we'll have some time to kind of work on those together. So in my slides, I have 3 kinds of code. There's SPSS code, SAS code, and R code. And there's these 3 codes for every activity. So the expectation is not that you are familiar with all 3 of these languages, but instead that you are prepared with one of these languages, and then you just follow along with the code that goes to your language. You got access to a GitHub that has all of the data files, as well as the process files and some miscellaneous PDFs and papers that I've recommended to people previously, just based on questions. And then one thing that I want to acknowledge is that these workshops, even though it's just 3 days, it's a lot of material all in one go. So I teach almost this amount of material in an entire quarter at UCLA. So you're getting a lot of information at a very short period of time. So if you're determined to stick it through all of this, it's going to require a lot of stamina. One of the things I really like about the way that SAS Horizon does their workshops is that you also get access to the recordings. So if you find yourself partway through a day and you're just like, I'm not getting this, don't worry, you can always circle back to this material in the weeks following the workshop. So for many people, you might be familiar with the material up to some certain point, and then the real learning begins. And just be patient with yourself. This is a lot of information, and it's really here to give you access to that information. And hopefully you'll be learning the entire time, but also be patient with yourself because it's a difficult way to learn, I think. Okay, a couple things that we do not cover, but I am always happy to answer questions about these things because I think for some people, you come for one thing and then you realize, oh, this might apply in all of these fun situations. So we're going to stick to fairly simple models and designs. So we're mostly going to be dealing with continuous outcomes in cross-sectional or experimental data, meaning that unless the group kind of votes to cover within subject designs, which is like my area of expertise, then we won't be covering that within the workshop. I have recently been talking to the Statistical Horizons about doing like a one-day short training on within subjects design. So if that's something that's interesting to you, let me know, let Statistical Horizons know, so that we can get that coordinated. I also want to mention, so this workshop is specifically using what's called statistical mediation analysis. There is another workshop that's hosted by Statistical Horizons that Tyler Vanderweel teaches, and that's all about causal mediation analysis. These two names are quite misleading, and I actually have a whole chapter on this, but it's different kind of frameworks for thinking about how to estimate these models. So Tyler's course covers more of like the counterfactual or potential outcomes approach, directed acyclic graphs, that kind of thing. But we're going to stick with pretty simple like linear models. And the statistical part of mediation analysis is really focused on the inference. Everything that we do in this class will use ordinary least squares regression, and then at the end of the class, I'll talk a little bit about some of the differences with SEM. And then we won't do anything with dichotomous outcomes, though Process, the tool that we are using, does estimate models with dichotomous outcomes. And then we won't deal with anything with multi-level data, but there is a tool that's quite similar to Process called ML-Med that is, I think it's only available in SPSS. But that is kind of like the go-to tool for multi-level mediation if you're interested in that. And although the kind of content that I'm teaching is not really software specific, we are going to be using this process macro to make a lot of our lives easier. This macro kind of does a lot of the heavy lifting for us in terms of doing things like bootstrapping or calculating conditional effects. Anyone who's tried to like do a very thorough moderation analysis with just an ordinary least squares regression program probably knows you have to like re-estimate the model multiple times to get everything that you want out. And that's kind of a headache. So we're going to be using Process. Okay, and then the last thing that I want to do is point you to a really, really wonderful resource. This is the book Introduction to Mediation, Moderation, and Conditional Process Analysis by Andy Hayes. It's in its third edition now, and for our R users, the third edition is the only one that has the R version. So the R version was just released very recently in 2022. I guess that's like 2 years ago now, so maybe not very recently. Feels recent to me. And the editions have really grown quite a lot as they've been released. So I do highly recommend using the third edition, which is it's a really wonderful book. For many of you who, if you're at a university, you might double check if your university has a copy of the ebook. Our university does, and so when I teach this course, most of the students use the ebook, so you can get it for free. Guilford isn't paying me, so I can say that. Super. So we will continue on with an example, and we're going to carry this example into our mediation section. So this example comes from a paper that was published in 2014 that was looking at harassment, particularly of immigrant adolescents. And this paper, as you may be able to tell from the title, included mediation analysis and moderation analysis in their understanding processes and conditions. So we're going to start with this example in just a mediation context, but then we will, or in a linear regression context, but then we will expand it out into a mediation. So the data for this study is available in the data folder that's on the GitHub link. And that's where you'll find the data for all of the studies that we'll use. You might want to just download everything kind of in one go. so that you don't have to kind of individually download files. It's not too big, I promise. So the data that we're looking at is 330 cases, and it's 7th to 9th grade students in Sweden. They're measured at 2 time points, so once during spring term, and then again a year later. And all of the students that were measured are first or second generation immigrants who reported some level of ethnic harassment, especially while at school. So if you open the data, you'll see there are a lot of variables. So I just want to walk you through what those are. The first variable is called harass, and this is a 6-item measure of ethnicity-related harassment. It's measured on a scale from 1 to 5 and is measured only at time 1. We also have a measure of positive relationships with teachers. This is also a 6-item scale, and it's scaled 1 to 4 and also only measured at time 1. Then we have a number of measures that are at time 1 and time 2. And so you'll notice in the variables in the data set, there is like SE1 and SE2. So SE is self-esteem using the Rosenberg self-esteem scale. And SE1 is measured at time 1 and SE2 is measured at time 2. We also have measures of depression, which is a 20-item scale that's specifically designed for children. This is also measured at time 1 and time 2. We have a measure of perceived academic failure at school. And so this is not an actual grade that a student is getting, but rather their perceptions of how they're doing in school, also measured at time 1 and time 2. And then we have a measure of their satisfaction in school, measured at time 1 and time 2. So in general, the way that I've kind of set up all of these data sets is so that higher means more of the thing. So higher does not always mean better, because higher harassment, maybe not better. But when you look at the variable name, it should be somewhat intuitive what a higher or lower score means. Just because I know we're hopping into a lot of different data contexts within this course, this might not be something that is super familiar to you. I try to keep the examples things that are relatively intuitive and don't require like a deep background in psychology to understand. But again, if you're looking at these variables and you're thinking, gosh, I don't really remember the directionality, then the typical way to think about it is higher is more. So higher scores is more satisfied with school, more academic failure, more depression, more self-esteem, more positive relationships with teachers, and more harassment. Excellent. So depending on which software you're using, you will have to do a little bit of a different thing. So for our SPSS users, you can just open the .sav file, and then it's like ready to go. For our SAS users, there is a SAS program that you have to run, and this will save a temporary work data file. So there will be a harass file, and you just have to run that file, and then it will save the data for you. And then for our R users, there are a lot of different ways to read in files in R. So if you have a preferred way to do it, you're more than welcome to. But otherwise, the method that I recommend is you can essentially save, here's the location of where this data set exists within your computer. So you will have to change this depending on where the data set is on your computer. And then you can use this read.csv function to save the harass data into your environment in R. And all of the data sets have the variable names as the first line. So you have to set this argument header equals true so that it knows that the variable names are the first line. Otherwise, it will think all of your data are strings and it will get very confused. So if you're following along, I want you to take just a minute to load in the data. One thing that I'll mention is that these are not the actual data from the study. They're generated to produce similar results to the study, but they are not the actual data from the study. So if you find something really interesting, I'm sorry, it's not. It's all computer generated. Okay, so just a couple notes for our R users. I try to, for the purposes of this workshop, I try to use as few packages as possible, just because I know that when we use packages, there's like updates and sometimes you have to install the package. But for the purposes of making nice summary tables and graphs, I use these three packages, so Mosaic, ggFormula, and JTools. So you may want to just install these packages now so that you have them running. And then again, to load your data, you can save your file path or just stick it into the read.csv function. And again, especially in R, but also in SPSS and SAS, there's usually multiple ways to do the same thing. So if you have a preferred way, feel free to deviate away from my way. I'm just here to give you some way to do something. Excellent. So for our SPSS users, I'm going to be giving you SPSS syntax. And so I'm not going to show every time how to like point and click to your options. It's a lot of work and it's not always reproducible. So so the way that I'm providing the instructions in SPSS is in syntax. If you haven't used syntax in SPSS before, then you can go to File, New, and Syntax, and then essentially a window will open, and that's where you can write the syntax or copy paste from the slides. And here you can type your commands into the window and then use this green run button, or if you're on a PC, Control R, if you're on a Mac, Command R, will run the code on the line that your cursor is on. Or if you want to run multiple lines of code, then you can highlight multiple lines of code and then either press run or Control R. So everything that we'll be doing today is with syntax. Excellent. So I want to start with just a quick review of regression analysis. We're going to be using regression for everything that we do in this class. And regression is used in a lot of different contexts as a means for modeling the relationships between variables. There are, of course, other methods for doing this. But linear regression, I think, is kind of a shared language across a lot of different fields. And it has really nice and lovely connections to some of our most basic tests like independent group t-tests and ANOVA. And ultimately, regression analysis is really built on the foundation of correlation, and specifically Pearson's correlation. So you can start with just looking at the correlation. We're going to look at the correlation between positive relationships with teachers and satisfaction with school. And just as a reminder, the SPSS code is in the black box, R code is in the gray box, and SAS code is in the white box. So if you have this data set up, you should be able to open and run this code just to estimate the correlation between these two variables. So here, positive relationships with teachers and satisfaction with school. So a kind of core way of representing these relationships visually is with a scatter plot. And here I've given code for creating scatter plots in SPSS, SAS, and R. And the basic idea that we are thinking about with the scatter plot is we have positivity of student-teacher relationships on the x-axis, satisfaction with school on the y-axis, and then the dots here represent the individuals and their scores. And in the graph on the left, I've done some binning where individuals that have the exact same score essentially get a little bigger dot. An alternative on the right here is you can also use transparency to reflect kind of overlap among participants. And the basic idea of linear regression that we're going to work with is if you had to draw a straight line that goes through this plot that best fits the relationship between these two variables, where does that line go? And this is exactly the problem that ordinary least squares regression solves, is it comes up with a kind of rule for describing what best is, and then provides a solution. So our goal in fitting an ordinary least squares regression, we're going to start with a simple linear regression, which means that there is one predictor variable. Simple in math means one. So if you see things that say simple in a math context, it's not that it's meant to be easy or trivial, but just that there's one of something. So we often talk about simple mediation analysis, and that's when we have one mediator, not that it is simple or easy. So the basic idea here is that I'm going to represent our linear regression equation in two different ways. One way is I'm going to have our outcome variable yi on the left-hand side, and our sample estimates b0 and b1. This is our intercept and slope. The slope is the relationship between x and y, and then we have a residual. And so we can also represent this in terms of just thinking about what the predicted score for y is. So when I put a little hat over the y here, this means the predicted score, and you'll notice that that drops off the residual on the right-hand side, because the residual helps it make it the real score, the observed score, but the hat part means just the model. And the residual we can think of as the difference between the observed score and the predicted score. So the basic idea in linear regression is that we want to have some kind of criteria that says, well, what is the best fit? And in this case, ordinary least squares regression gets its name from this basic idea that we want to minimize the sum of squared residuals, which is to say I could take each of these residuals, square it, and then sum across all the individuals in the data set. And that will give me my sum of squared residuals. And I want to find the B0 and B1 that minimize these values, specifically the sum of squared residual. So we can also represent a linear regression in a visual form, and this is kind of building up to how we will do this with mediation analysis specifically, where a kind of full and complete version of this equation would look like what's here on top, which is to say I have my predictor x predicting y, and the arrow here is representing the relationship, so it's called b1, which corresponds to our slope. I also can have the intercept in my visualization using a triangle with a little 1 in it. This comes from the structural equation modeling literature. And then the path for this is b0. And then I have my residual, and the residual doesn't have its own coefficient, so it just gets a 1 for the size of the path. A lot of the time, though, we'll use a shorthand where we're just focusing on the parts of the visualization that are useful to us. So, so here I have just kind of what I'll use for shorthand, which is x predicting y and the slope being b1. So I've dropped off the intercept and I've dropped off the residual. And that doesn't mean that they're not there. It just means that I'm not putting them in my visualization. And in particular, one of the things that is important to understand about these kinds of graphs or path diagrams is that the arrow is meant to represent what is a predictor of what in our regression models, not necessarily that something is causing something else. So by saying X predicts Y, that doesn't necessarily mean or provide evidence for X causing Y. So the directionality of these arrows is really just meant to represent what's on the left-hand side and what's on the right-hand side of a regression equation, not necessarily to make particular claims about cause. So I'm going to show you a little example in SPSS, and then we'll walk through SAS and R as well. But we're going to start by fitting a simple linear regression. And here in SPSS, we use the regression command. I've included some extra options. So the statistics option essentially allows you to change what all is included in the output. And so you always want to include the defaults. And then here I've added in CI so that we can get confidence intervals for our regression coefficients. But the core of this command is on the right-hand side here, which is that the dependent variable is satisfaction in school. And then we said method equals enter, and then our predictor variables, which is positive relationships with teachers. So here we're estimating the relationship between satisfaction in school as our outcome and positivity of teacher-student relationships. And the point that I want to emphasize here is that the solution that we get here, which is that the intercept is 2.245 and the slope is 0.531, this gives us a sum of squared residual of 125.433. And what we know from the way that ordinary least squares regression works is that there's no other pair of B0 and B1 that would give us a smaller sum of squared residual within this sample. And so this is a unique solution. So this is our best fit model from ordinary least squares regression, assuming that there is a linear relationship between X and Y. In R, we can do the same thing where we have the process of doing this is a little bit different, where typically you're going to fit a model object and you're going to save that. So we'll use the LM command for pretty much everything in this course. And you'll use LM and then the outcome variable, which is status1. Tilde is kind of like, think of it like the equal sign in the regression equation. So you want your outcome on the left-hand side and then your predictors on the right-hand side. So here I have status1 tilde pos rel. And then you have to tell R what the name of the data set is that you're using. If you save this object and then you take the ANOVA of that object, then you'll get the sum of squared residuals that we saw in the output from SPSS. So you'll notice in SPSS and SAS, all three of these kind of chunks of the model output kind of come out automatically. But in R, you have to kind of request each individual chunk. So you'll use ANOVA in order to get the ANOVA table, and then a summary model gives you a lot of information, including the coefficients, as well as their standard error, t-value, and p-value. Are there any questions about just fitting the linear regression models in the software? Okay. Feel free to post in the chat if you have other questions. So going back to our scatter plot, we have the positivity of student-teacher relationships on the x-axis and then satisfaction with school on the y-axis. And here, I've added in our best fit line. So this is the line that ordinary least squares regression has said, okay, this is the best fit line to your data. The intercept of this line is 2.245 and the slope of this line is 0.531. Then we can see that cases that are above the line, these are cases with positive residuals, and any cases that are below the line, these are cases with negative residuals. One of the things that I'll emphasize a lot in this class is interpretation. So ultimately, for most of you, I think, doing these kinds of models, it's not enough just to be able to run the model and get the output, but ultimately the product that you're shooting for is some kind of potentially written or verbal product where you describe the results, right? So whether it's a peer review publication or a presentation, whether that's like at a conference or to your lab group, or for those of you who are biostatisticians, maybe to the folks that you are working with, ultimately we have to translate the numeric output from our analysis into words. And I focus on this a lot because it is, I think, one of the more difficult parts of doing this kind of work is interpreting the results correctly. And so you'll see that I focus a lot on interpretation. So in our simple linear regression, we get an estimate of our slope, B1, which we estimated to be 0.531. And you're probably idea of a slope, right, which is for every 1 unit increase in X, this is the predicted increase in Y. One of the things that I want to emphasize, though, is especially for those of us who are working in non-experimental contexts, it is important not to translate that increased language into an actual interpretation, because we are not, in fact, increasing anybody's score. We're not taking people and changing them a lot of the time, but often we're, like in this example, observing people who have different scores on our positivity. So here our B1 interpretation would be the estimated difference in Y between two cases that differ by 1 unit in X. And the sign of B1 speaks to the sign of the association. So we can think about for two individuals, let's say maybe one person has a score of 2 and another person has a score of 3. What is the predicted score for the person with 2? And what is the predicted score for the person with 3? And then what is the difference between those predicted scores? So here we might say for two kids that differ by 1 unit on positivity of their student-teacher relationships, they're estimated to differ by 0.531 units in satisfaction with school, where the kid that's higher on positivity of relationships is estimated to be more satisfied. So this is an interpretation that doesn't include that increase-decrease language, because in this specific design, we're not observing children over time, right? We're not watching their positivity of student-teacher relationships change or increase or decrease, but rather we're thinking of two hypothetical children who differ by 1 unit on their predictor variable and how much they're expected to differ on the outcome. Excellent. And then for our intercept, we can think about the intercept as the estimated value of Y when X is 0. And in this case, the positivity of student-teacher relationships variable only goes from 1 to 4. And so in this specific context, I likely wouldn't write an interpretation of this coefficient in my paper, though we'll talk about methods for making sure that B1 is or B0 is interpretable using mean centering. But it is important to always know and understand the range of your predictor variables so that you do not extrapolate beyond the range of your data. Excellent. So I'm going to expand out to multiple predictors, where we might not just have one predictor in our model, but we might have as many as we want, for example, K predictors. And we can represent our linear regression in this kind of expanded version, or oftentimes you'll see this summation notation, which means just summing across all of the Ks. So going from K equals 1 to capital K, and then summing up BK, XKI. And we can represent this in our visual shorthand by having each of our individual predictors and their slopes along their arrows predicting Y. And again, just because I'm using the shorthand representation of this linear regression doesn't mean that there's not a residual and an intercept. It just means it's not in the figure, right? So when we do this, and here I can set up a model where, again, we are predicting satisfaction in school, and now I've added in 2 additional predictors. So we originally had positive relationships with teachers, and I'm going to add in harassment and self-esteem at time 1. And now what we'll notice is that when we fit this model, the sum of squared residuals is smaller than the previous time that we fit it. So I think last time it was like 200 and something. Now it's 100 and something. And again, this is a unique solution in that there's no other set of B values that would give us a smaller sum of squared residuals. And now we can think about, okay, what did these individual coefficients mean in the context of this model? We can do this also in R. So in R, oh, sorry, I was going to mention one thing in SPSS if you haven't done this before. So in SPSS and SAS, when you're adding in new predictors, you're going to just include a space in between each of the predictors in your code. So here in SPSS, we say method equals enter and then pause rel space harass space SE1. In SAS, you're going to do the same thing where you're going to say POSREL space harass space SE1. So you don't need any special notation. In R, you're going to use plus signs in between each of your individual predictors, just as a kind of difference between SPSS, SAS, and R. But just like we did before, we're going to save the linear model and then feed it into two functions. One is the ANOVA function so that we can get an estimate of the sums of squares, and then the summary function so that we can get the coefficient estimates. So now what we can do is think about how these individual coefficients are interpreted. And when we are doing a multiple regression analysis, we can think about holding constant all of the other predictors when we are interpreting one specific predictor. So let's think about just B1 for the moment. We can think of this is called a partial regression coefficient. The name is kind of derived from partial correlation in that we're partialing out the other predictors prior to estimating the relationship. And this is quantifying how differences in the positivity of student-teacher relationships are related to differences in satisfaction with school when all other predictors in the model are held constant. This might also be described as statistically controlling for all other variables or adjusting for. There's a lot of language that's used around this that is all kind of acceptable. So here, we might say for two kids that are the same on all predictors except for positivity of their student-teacher relationship, but differ by 1 unit on that positivity, they're expected to differ by 0.472 units in estimated satisfaction with school, where more positivity corresponds to higher satisfaction. We can try this with B2 as well, where we might say for two people that are the same on all predictors except ethnic harassment, who differ by 1 unit on harassment, they're expected to differ by 0.145 units in estimated satisfaction in school, where higher harassment corresponds to lower satisfaction. So in this example, the B2 coefficient is negative. So that interpretation of the sign that comes at the end is really important because when we use this kind of differ language, the directionality of the effect is not always communicated. Okay, any questions on the interpretation side of things? I'm going to cover inference and then we're going to take a little break. So I'm gonna kind of breeze through statistical inference just to make sure that we're kind of all on the same page. But if you have any questions about this, feel free to ask. So basically in the notation that I'm using, if the coefficients themselves have kind of no extra anything, that means they're the sample estimates. Just because for most of this class, we're working with the sample estimate, so I've picked a notation that's easiest. And then I'm using this notation where when we put a tilde over a coefficient, that represents the population value. So the kind of the true, T for tilde, true value. And the core thing that we're thinking about when we're thinking about inference is that there is some underlying kind of true value of all of these coefficients, but we don't know it. We only have a random sample that may deviate away from our population value. And this could be due to random sampling, random assignment variation, or measurement error. And so we have to use an inferential process in order to make conclusions about what's going on in the population. So one of the most common inferential processes is called null hypothesis significance testing. And the basic idea is that we can set up what's called a null hypothesis about any parameter of interest, and then assume that that null hypothesis is true. Then we can derive what the probability of observing essentially our sample or something more extreme is under that null hypothesis. If that probability is sufficiently low, then we would reject the null hypothesis. So for our purposes, we're going to be focusing mostly on individual regression coefficients. So here we could assume that the true population B1 is equal to 0. And then under that null hypothesis, B1, the sample value of B1 divided by its standard error, follows a t distribution with the degrees of freedom being the degrees of freedom residual from the model. And SB1 here is the estimated standard error of B1. So we could then use a t distribution to find a p-value that we would then reject if it is less than or equal to some alpha level that we've predetermined. And at least in my field in psychology, a lot of the time we use 0.05. That's pretty arbitrary, but just whatever significance level you tend to use. Our software does this for us, which is really quite nice of the software. So when you're reading the output, this is exactly what it's doing, which is for each of the regression coefficients, it calculates a standard error. You get a t-value and a p-value. And I'm not entirely sure why this is this way. But a lot of the time, especially our SPSS users, when you're looking at the output from SPSS, it's not immediately clear what the degrees of freedom are to go along with this t-value. And those degrees of freedom can be found in the ANOVA table, and they're the residual degrees of freedom. So the degrees of freedom to report with your statistic, your t-statistic, is this degrees of freedom up here. So you might report something like this, where you report a coefficient, standard error, t-value. The degrees of freedom here are the degrees of freedom residual. And so for our B1 coefficient, our p-value is pretty low. P-values are never 0, even if the computer tells you that they are. It just means that they're very, very low. So in this case, because the software reports out to 3 decimal places, I might write something like p less than 0.001. So in this case, we would reject the null hypothesis in favor of the alternative, which is that the population coefficient is not 0. But for our coefficient for harassment, the p-value is 0.108, which if we're using a 0.05 alpha level, we would then fail to reject the null hypothesis. So based on this, we would make some inferential statements like this, where we might say 2 kids equal in ethnic harassment frequency and self-esteem, but who differ in the positivity of their student-teacher relationships, differ from each other in satisfaction more than can be explained by chance, right? So the idea of more than can be explained by chance is derived from this idea of just sampling from a null. That's a weird way to say that. Sampling from a population where the null hypothesis is true. So this seems very unlikely, even in the case when we're doing that kind of sampling. So then we might say that the observed and statistically significant positive partial relationship tells us that kids with more positive student-teacher relationships are more satisfied with school. We might also say for our second coefficient for harassment, 2 kids equal in the positivity of their student-teacher relationships and their self-esteem. So these are the other 2 predictors in the model, POSREL and SC1, but who differ in ethnic harassment frequency, do not differ in their satisfaction any more than would be expected by chance. So this idea that this is still a fairly probable outcome if we were sampling from a population where the null hypothesis was true. We can also do interval estimation and confidence intervals. Confidence intervals are very, very popular in mediation analysis, so we'll be using these a lot. The basic idea here is that we can take our estimate and subtract out usually 2-ish, it's not exactly 2, but 2-ish times the standard error, and then take our estimate and add 2-ish times our standard error to get a 95% confidence interval. And then typically, if this confidence interval includes 0, we would reject the null hypothesis. If it does not include, if it includes 0, we fail to reject the null hypothesis. If it does not include 0, we retain, oh my gosh, I keep saying this backwards. Okay, so for our example, like our positive relationships, this confidence interval does not include 0, and we would reject the null hypothesis, right? So here, we already knew that we rejected the null hypothesis because the p-value is less than 0.001. But we can also make a claim like this, where we would say we can be 95% confident that the true value is somewhere between 0.363 and 0.581. There's a lot of finickiness about interpreting confidence intervals. Essentially, like, the safest thing to do is always use the word confident. Don't use the word probability or likelihood or anything else, because the difficulty is that the randomness is in the interval, not in the parameter. So this word confident is doing a lot of mathematical heavy lifting for us, where we'd really say, like, in 95% of random samples, the confidence interval that we generate will capture the true population value. That's really, really long. So this word confident is doing a lot of mathematical heavy lifting. Don't replace it with anything. Always use the word confident, and then you'll be safe, which is fine. Okay, and then to do this in R, actually you can feed in your model object. So here I've called it multimodel for multiple regression model. And if you feed it into the conf_int function, then it will give you a confidence interval for each of the regression coefficients. You'll notice that these are identical across the software that you use. So there's no reason to use one software over another in terms of one is not more correct than the other. You're getting the exact same answer.